All right, so this is the sprint round from 2022, practice competition 2. We're going to take a look in this video on problems 26 through 30. We're going to do groups of 5. So the first problem is actually a really simple problem, really basic problem that they tried to sneak in at the end thinking you weren't going to get there. So Mandeville has one standard quarter and one special quarter. The special quarter has heads on both sides. He flips it. He picks one quarter randomly, flips it 3 times, and he gets heads every time. What are the chances that he got, or he randomly picked, the special quarter? Well, so here's the thing. If I get the special quarter with a head and a head, we're going to end up with, and I don't have to write the heads every time, you're going to end up with 8 total heads. Okay. Well, what happens if I have a tail and a head, the standard quarter? We will again have a total of 8 different options. Now, and you don't have to draw out the counting tree, you know it's going to be 8 options. And the only way to get 3 heads is if you get head every time. So that's 1 out of your 8 options. So right now, if you get 3 heads in a row, there are only 9 different ways to get those heads. And 8 of them come from the special quarter. So the odds that you pick the special quarter is 8/9. All right, let's take a look at, not this problem. How about this problem? Oh, no, I didn't set this up. Oh, I love this problem. This problem's really cool. This is a pretty special Pythagorean Theorem problem that we got right here in 29. So we have a circle that is hidden behind these 3 blocks. And we want to know what is the largest possible circle that we can draw that is hidden behind these 3 blocks. So let's get to it. So we know, I'm going to draw these blocks out a little bit bigger so it's easier to draw. So we know these are unit squares. And I know that my drawing is not perfect, but whatever, we will survive. And so, first thing we need to realize is that if we have a circle centered around M, well, that's not going to be the biggest circle possible, because I can take that circle, and let's see if I can grab it. It's tough to grab it. Oh, let's break it apart. So I can take that circle. And notice how, when I bring it down, I could have definitely made this circle bigger and still be covered by the 3 squares. So we automatically know that 1/2 is not going to be the largest possible radius that we can have. So the better way to think about it is this. We know that this distance here is going to be a chord inside the circle. So we're going to end up with, and this is where my drawing is unfortunately not wonderful. I actually did this problem on paper using a compass, and you would find out that this point right here, the circle goes through this point, and this point. All right, so then, right now I'm still kind of stuck because there's not much I can do. So when there's not a whole lot I can do, I'm going to start drawing stuff. I'm going to start drawing extra lines, see if that helps us. So I know the center is going to be on this line right here. So I'm going to draw the center. And it's about right. And so then I know, oh, wait a second. I have this point here, I have this point here. I'm making a triangle. And I know this is a right triangle. And so as soon as we're able to make a right triangle, and this is a good strategy, we know we're going to be living in the realm of a squared plus b squared is equal to c squared. All right, well, I know that this is 1/2 because we have a unit square and it tells us that M is the midpoint of AB. All right, but now let's take a look at what we've got here. I don't know the other 2 sides, but I do know that this distance right here is going to also be equal to this distance here. So if I can find a way to relate these 2 side lengths together, I might have a chance of getting this right. So if I don't know something, I'm going to call this x, because that's what we do apparently. So then, well, this whole thing here, this whole distance is 1. So that means this remaining side has to be 1 minus x. Well, that just means that this side length is also 1 minus x. So I can plug that into my Pythagorean theorem. Oh, this is so cool. So we have 1/2 squared plus x squared is equal to 1 minus x squared. All right, well, 1/2 squared is simply 1/4. Plus, we still have our x squared, which is equal to, now we have to be able to multiply a square binomial, but we can do that, and we will get 1 minus 2x plus x squared, using the rules of square binomials. So I can't help but notice immediately that I have an x squared on this side and x squared on this side, so I can cancel them out. So now, all right, just a simple train track problem, -1, so I get 3/4 is equal to negative 2x, and that's a negative 3/4 because 1/4 minus 1, well, that's negative 1 is farther from 0 than positive 1/4, so it's a negative. I'm going to divide by negative 2. Well, dividing by negative 2 is the same as multiplying by negative 1/2. So that means negative times a negative is a positive, so we're going to get 3/8 is equal to x. And boy, do I wish I would be done, but I'm not. Because what's typical of math counts problems is you're going to do the heavy lifting, and then you're going to have to do one last step. And they're hoping that you miss that one last step. I just found this side length right here, but I want the radius. The radius is 1 minus that short side length. Well, 1 minus 3/8 is going to be 5/8. And that is my final answer. That one was a pretty cool problem. The math behind it not too difficult, but you gotta make that connection with the Pythagorean theorem. All right. A triangular region having vertices 0, 0, 3, 0, and 0, 4 is rotated about the x-axis to find a cone, just like this. The same triangular region is rotated around a y-axis to form a solid cone. All right. What is the ratio of this first cone to the second cone? All right. So looking up here, first thing, what do I know about cones? Well, I know the volume, because we're talking about volume, is equal to 1/3 the area of the base. Well, the base is a circle, which is pi r squared. And then we're going to multiply it by the height of the cone as well. So we know that up front. So looking at this one right here, we have a base radius of 4. So that means we have the volume is equal to 1/3 pi, and the radius is 4 squared, and the height, well, the height is just going to be that 3. And it says a common expression units was common fraction. And I know I don't need to worry about pi, because when I express it as a common fraction, we're going to have a pi in the numerator or a pi in the denominator. Well, it's going to go away pretty quick. Same thing with the 1/3, so I'm going to have a 1/3 in the numerator and a 1/3 in the denominator. So all I really care about is this piece right here. So 4 squared is 16. 16 times 3 is going to be 48. All right, same idea for this one right here, but this time we have a radius of 3. So we have our 1/3 pi, radius of 3 squared, times our height is now 4. All right, so 3 squared is 9. So we have 9 times 4, which is 36. So we get a ratio of 48 over 36, but we can't write that right because clearly that's not right, because we have a fraction that can be reduced. Well, what goes into both of them? 12 goes into both of them, so we'll end up with 4/3. And that is the final answer. All right, let's take a look at the next one. Oh, arithmetic sequences. When I see arithmetic, you know what I think? I think linear. So we have an arithmetic sequence, and we're going to get to deal with some linear stuff. All right. So, and we know that the sum of the sequence is 273, and we have a total of 21 numbers in the sequence, and the fifth number is 7. We want to find the 49th. Well, what I really want to do is find the equation for the numbers in our arithmetic sequence, and then plug in 49, and that will give me the 49th number. All right, so I know that I have 1, 2, 3, 4. The next number is a 7. And I also know that the average of all of these numbers has to be 273 divided by 21. That's 273 divided by 21. 21 goes into 27 once, and we're going to carry 6. And then 21 goes into 63 3 times. So the 13th, so the average number has got to be 13. And to make things even better, we know that since we have 21 numbers, the 11th number has to be 13. So there's my 5th, 6th, 7th, 8th, 9th, 10th, 11th. Well, that means we're counting by ones. That's the only way this works. And going backwards, we have 6, 5, 4, 3. But here's the trick. This number right here is the first number in the sequence. If I'm looking at y equals mx plus b, this b value is the 0 term. So I need to go back one more, and so I know the 0 term, that y-intercept, is in fact 2. And my slope is 1, and I know that I want the 49th number, so we have 49 plus 2 is 51. All right. When you see arithmetic, you know that's a problem you want to do, because it cannot be terribly complicated and it's not going to be very long. It's just going to be y equals mx plus b. All right, last one for this sequence. The landlord of an apartment building needs to purchase enough digits to label all of the apartments from 100 to 125 on the first floor and 200 through 225 on the second floor. The digits, unfortunately, can only be packaged in, well, they have a complete set of 0 through 9. So we need to know how many packages that we have to purchase in order to label all of the apartments. I think a more fun question would be is how many leftover numbers you would have after you went through this, but that probably wouldn't be a sprint round problem. All right, so let's logic ourselves through this a little bit. I know we have numbers 100 through 125 and 200 through 225. So what number will we see the most of? Because that's the one that we're going to have to buy the most packets for. And clearly it's either going to be a 1 or a 2, because we have a 1 or a 2 in the hundreds digit for each one. But then I also realize it can't be 2, because in this second floor, we only go to 25. So half of the 20s we don't have to worry about, where we have to worry about all of the teens, which will require an extra 1. So we want to know how many 1s we're going to have in this whole thing. So let's break this apart. So if I'm talking about the hundreds, from 100 through 109, we are going to have a total of 11 ones, because we're going to have 10 in the hundreds digit, and then we're going to have 1 for 101, 1 in the tens or units digit. So how about from 110 through 119? Well, from 110 to 119, we're still going to have 10 here. We're also going to have 10 here, which also means we're going to have 1 in the units digit for a grand total of 21. All right? How about from 120 through 125? Well, we're going to have 5 in the hundreds digit, and we're going to have 1 in the ones digit when we get to 121. Fun number, palindrome, and a square number. And so that's going to give us a grand total of 6. 5 plus 1 is 6. How about the 200s? Well, from 200 through 209, we're only going to have 1 for 201. From 210 through 219, we're going to have that 11 again, because we're going to have 10 in the tens for the tens digit, and we're going to have 1 here. And then from 220 through 225, that's a 25, we're going to only have 1. Oh, okay. So let's add these together. So altogether, this is 13. Altogether here, well, so that's 32, that's 38. 38 plus 13 is 51. And that's how many packs you're going to have to buy. It seems kind of wasteful, though. I think they should sell them by individual numbers. How about you? All right.